What happens if the chip war is no longer about the chip? What do you think will decide the future of the semiconductor industry? What if it is not smaller transistors, not more expensive lithography machines, and not a giant chip factory worth tens of billions of dollars, but instead a piece of glass so thin that almost nobody can even see it? Sounds ridiculous, right? For years, whenever people talked about the chip war between the United States and China, most people immediately thought of silicon, TSMC, ASML, and massive EUV machines that only a very small number of countries can access. But behind that loud and very public battle, another path has been quietly forming, and it could change the entire way we understand semiconductor power. China is said to have poured more than $1 billion into a field that sounds surprisingly ordinary at first: glass substrates for chips. Not window glass, not phone glass, and definitely not the kind of glass you see in a kitchen. This is an extremely precise engineering material designed to become the foundation for the next generation of massive AI chips. And if that does not sound serious enough, just look at the bigger picture. While Washington is focused on blocking China's access to advanced lithography machines, especially ASML's EUV systems, China seems to have turned its eyes toward a different battlefield, not printing the smallest transistors, but connecting many smaller chips together into a more powerful system. That is what makes this story so fascinating. Modern AI chips are no longer just a single piece of silicon. They are becoming more like a miniature city, where multiple chiplets, memory stacks, interconnect circuits, and signal layers all have to work together like one unified brain. And underneath all of those components is a substrate. That substrate has to hold everything in the right position, move signals extremely fast, handle heat extremely well, and avoid warping when the system runs at high power. For decades, the industry has used organic materials, basically a very sophisticated type of engineered plastic. But as AI grows too fast, that plastic foundation is starting to hit its limits. So what if China does not need to beat TSMC at every semiconductor node? What if it does not need to immediately own the most powerful EUV machine? What if instead it finds a way to control the very floor that future chips have to stand on? That is why the story of glass is not small at all. It is not just a new material. It is an industrial strategy. It is a way to move around the door that the West is guarding very tightly. And if any country masters glass substrates for advanced packaging first, that country could hold an extremely important position in the AI era. But the big question is, why does glass matter so much? Why are companies like Intel, Samsung, TSMC, Corning, and many Chinese firms suddenly paying more attention to this field? And is this massive investment in glass substrates truly a turning point in the chip war, or just another overhyped technology bet? Before we get deep into the story, if you enjoy analysis videos like this, do not forget to subscribe so you do not miss what comes next. When the chip war moves down to the foundation, for years America's strategy toward China in semiconductors seemed very clear. If China cannot access the most advanced chip-making equipment, then it cannot produce the most powerful AI chips. And if it does not have the most powerful AI chips, it will fall behind in the race for artificial intelligence, supercomputers, self-driving cars, robotics, military systems, and the data infrastructure of the future. On paper, that logic is very strong. ASML's EUV machines are among the most important tools for producing advanced semiconductor nodes. Intel has also made it clear that glass substrates are one possible path to keep expanding the number of transistors inside a package. But the semiconductor industry itself still depends heavily on both front-end manufacturing and back-end packaging. But the problem is that the chip industry does not have only one path to becoming more powerful. As shrinking transistors becomes harder, more expensive, and slower, companies are looking for another direction. Instead of forcing everything into one single chip, they split the system into smaller chiplets and connect them through advanced packaging. You can think of it like this. Instead of building one giant skyscraper, they build many specialized buildings and then connect them with tunnels, bridges, electrical systems, data lines, and a central control system. If those connections are fast enough, stable enough, and dense enough, the entire chiplet cluster can work like one massive processor. That is when advanced packaging becomes the new battlefield. Names like TSMC's CoWoS, Intel's EMIB and Foveros, and 2.5D and 3D packaging solutions are no longer just supporting technologies, they're becoming core parts of the AI race. MediaTek has also recently emphasized that it supports both TSMC's CoWoS and Intel's EMIB, showing that AI chip customers are paying more and more attention to packaging choices, not just manufacturing nodes. And when packaging becomes the center of the game, the substrate underneath the chip also becomes a matter of survival. A substrate is not glamorous, it does not get announced on stage like the latest GPU. It does not appear in laptop ads or data center commercials. But it is like the foundation of a house. A house can have beautiful furniture, luxury glass doors, and a modern electrical system, but if the foundation sinks, the whole structure is in danger. AI chips work the same way. The chiplets can be extremely powerful, and HBM memory can be incredibly fast. But if the substrate cannot stay stable, if signals get noisy, if connections shift, or if heat causes the material to warp, the entire package becomes limited. For decades, organic materials have performed this role very well. They are cheaper, more familiar, easier to integrate, and supported by a massive supply chain. But AI is pushing everything to the extreme. Packages are getting larger. Interconnect density is getting higher. Power consumption is becoming enormous. Heat is becoming harder to control. And when all of these variables increase at the same time, organic materials begin to reveal their weaknesses. They can expand or contract with heat, they can warp, they can limit connection density, and they can force engineers to design around the weaknesses of the material instead of designing what they actually want. But to understand why this matters so much, we need to look at the core of the entire story. When the plastic foundation of AI chips starts hitting its limit, imagine a modern AI processor not as a tiny chip sitting neatly on a circuit board, but as a miniature ecosystem. Inside it, there are multiple processing dies, multiple high-bandwidth memory stacks, many signal layers, and billions of microscopic connections. Everything has to work in sync inside an environment with high temperature, high current, and extremely fast data transfer speeds. Any tiny misalignment can become a major problem. For an ordinary user, a deviation of a few micrometers does not sound like much. A micrometer is much smaller than a human hair. But in the world of advanced chips, a tiny change can mean the difference between a stable connection and an expensive manufacturing defect. As the package gets larger, material distortion is no longer just a local issue. It can accumulate across the entire area. A substrate that is slightly bent, slightly expanded, or slightly misaligned can make chiplet attachment, circuit connection, signal transmission, and thermal management far more complicated. That is the problem with organic substrates. Not because they are bad. In fact, they have helped the semiconductor industry grow for decades. But every material has its era. A bridge designed for horse-drawn carriages may still stand when cars appear, but when heavy trucks, non-stop traffic, and much higher loads arrive, that bridge needs to be replaced or reinforced. Organic substrates are the same. They were born for a period when chips were smaller, packages were simpler, heat was lower, and connection density was much easier to manage. When AI enters a new phase, everything changes. Chips for data centers do not just need to be a little faster. They need to handle large language models, computer vision, autonomous robots, scientific simulations, self-driving vehicles, and a long list of applications that require enormous amounts of data. That forces chip designers to place more chiplets closer together, move data faster, and reduce latency even further. But the more they push connection density, the more organic substrates become a bottleneck. Intel has described glass substrates as a path that can improve flatness, thermal stability, and mechanical stability, while also enabling higher interconnect density compared with today's organic substrates. This is why glass substrates are seen as the next step for large packages used in AI and data centers, where performance and bandwidth demand are rising extremely fast. This is the key point. While most people are still looking at transistors, packaging engineers are looking down at the foundation. And if that foundation cannot keep up, the entire AI ambition will be limited. Not because we do not know how to design more powerful chips, but because we cannot connect them well enough, stably enough, and at a large enough scale to turn those designs into real products. It sounds simple, but this small detail could change the entire game. What can glass substrates actually do? Glass in the semiconductor industry is not fragile like a drinking glass falling onto the floor. This is a material engineered for extremely high stability. What makes glass attractive is not just that it's harder or flatter. The point is that it has properties that match exactly what next-generation AI chips need. Less warping, better stability under heat, support for higher interconnect density, and potentially better signal transmission in large packages. Let's use a simple example. You may have seen heat-resistant glass cookware go from an oven to the outside environment without instantly deforming. Of course, semiconductor substrates are far more complex than that, but the material principle here is worth noticing. Certain types of glass can maintain strong dimensional stability when temperature changes. In AI chips, this is extremely important. Every time a chip runs under heavy load, the temperature rises. When the load drops, the temperature falls. That hot and cold cycle repeats thousands or even millions of times. If the substrate underneath expands or contracts too much, the microscopic connections are put under stress. Glass substrates help reduce that problem. They hold their shape better, warp less, and create a more stable platform for mounting many chiplets. For AI chips, this is like moving from a wooden floor that can expand when it gets humid to an engineered floor that barely changes even under harsh conditions. When the floor is stable, you can build more complex structures. You can place more components. You can route more signal lines. And most importantly, you can trust that what you put down will not move beyond the allowed limits. The next advantage is connection density. Chiplets only make sense if they can talk to each other extremely fast. If each chiplet is like one part of the brain, then interconnects are the nerves. The denser, faster, and cleaner those nerves are, the stronger the whole system becomes. Intel has said that glass substrates could significantly improve design rules for future AI and data center products. That is why glass substrates are not just a replacement material, they open up a new way of designing. If organic substrates force engineers to constantly worry about warping, flatness, signals, and size limits, glass substrates may allow them to think bigger. Packages can become larger. The number of chiplets can increase. Signal lines can become denser. And when the package becomes almost like a complete system, the line between one chip and a miniature computer starts to blur. But one important thing needs to be made clear. Glass substrates will not make silicon disappear overnight. Silicon is still the central material for logic, memory, and many other semiconductor components. What glass substrates can change is the packaging foundation where multiple pieces of silicon are connected together. So a headline like "Silicon is obsolete" should be understood in a strategic and dramatic sense. Silicon is not dead, but competing only through silicon nodes may no longer be enough. And this is where the story turns to China. China sees a battlefield many people overlook. From the Western point of view, China's biggest bottleneck is lithography. Without EUV machines, China has a hard time producing the most advanced chips the way TSMC or Samsung does. That is true. But true does not mean complete, because if the future chip race is not only about smaller nodes, but also larger packages, denser connections, and more stable substrates, then a country can try to build an advantage in the back end of the value chain. This is where glass substrates become a very interesting path. China has an advantage many people overlook: a massive display and glass industry. BOE is one of the largest display manufacturers in the world. For years, it has built up capabilities in processing large glass panels, controlling flatness, cutting glass precisely, managing yield, and operating huge production lines. Even though display panels and semiconductor substrates are not the same thing, the underlying industrial skills overlap in one important area: handling glass materials with high precision and large output. This is the interesting part. If a country already has large-scale glass infrastructure, it is not starting from zero. It still has to solve many new problems, but it already has industrial muscle. It understands surface control. It has experience running glass factories. It knows how yield can destroy profit margins. It has teams familiar with large, flat, thin materials that are sensitive to tiny deviations. When moving into glass substrates for semiconductors, those experiences do not automatically turn into victory, but they can shorten part of the learning curve. Industry reports suggest that many Chinese companies are accelerating in TGV or through glass via a technology that creates conductive holes through glass for advanced packaging. TrendForce has mentioned Chinese companies such as BOE, Ekent, and others in the context of China pushing glass substrate technology for advanced packaging. TGV is the heart of the problem. If you want to use glass as a substrate, you cannot just have a beautiful flat sheet of glass. You have to create conductive channels through it. Those channels have to be extremely small, extremely uniform, and extremely precise. Then they have to be coated or filled with conductive metal, usually copper. If the holes are not accurate, the signals are not stable. If the metal and glass do not bond well, temperature changes will create stress. If there is a microscopic crack, the failure may not appear in the factory right away, but only after the product has already been delivered to the customer. For an AI chip package worth tens of thousands of dollars inside a data center, that is an extremely serious risk. So, glass substrates are not a story of China buys glass and wins. This is a story about manufacturing capability, defect control, process accumulation, and the willingness to burn money for years before a real commercial product appears. That is why an investment of more than $1 billion, if industry sources describe it correctly, should not be viewed as a single research expense. It is a signal of a long-term strategy. Learn first, manufacture first, reach yield first, and lock in customers first. But no matter how promising a technology is, it means nothing if it cannot be produced at scale. The manufacturing nightmare. Why glass is so difficult? If glass substrates are so great, why has the whole industry not switched to them long ago? The answer is very simple. Producing them is extremely difficult. In the lab, a technology can look very promising. But inside a factory, it has to survive thousands of inspection steps, millions of handling operations, and the requirement for yield high enough to sell at a reasonable price. Semiconductors do not reward good ideas. Semiconductors only reward processes that can be repeated millions of times. Imagine you have a thin sheet of glass. You need to drill thousands, maybe even millions of tiny holes through it. Those holes have to be straight, uniform, and clean without cracking the glass and without creating hidden defects. Then you need to place conductive material inside those holes, make sure it bonds firmly, transmits signals reliably, and does not separate when temperatures change. Making one prototype is already hard. Producing it at scale with high yield is much harder. Organic substrates have one major advantage. They are easier to process. They are more flexible. They are more forgiving. Glass is not. Glass is strong, but it is also brittle. It is stable, but extremely sensitive to micro defects. A tiny crack created during production may not be visible to the naked eye. It might pass some early tests, but after many thermal cycles, that crack can spread and cause failure. This is the kind of risk chip customers fear, because failure in advanced packaging does not just ruin a cheap component. It can ruin an entire complex package containing many expensive chiplets. On top of that, glass substrates must be extremely flat. When chiplets are mounted onto the substrate, everything must stay within extremely tight tolerances. If the surface is not flat enough, the bonding process can fail. If heat deforms the substrate, the connections can be affected. If chemical or mechanical processing changes the surface, yield drops. So manufacturers do not just need to know how to make glass, they need to know how to make semiconductor-grade glass with precision, cleanliness, and stability at a completely different level. Intel has emphasized that moving from organic substrates to glass substrates is not a simple change, and that the substrate industry will have to remap itself around the new technology. That means equipment, chemicals, inspection processes, quality standards, supply chains, and even the way customers design packages all have to change. And there's one more barrier: qualification time. In semiconductors, a new material cannot simply prove that it works once. It has to prove that it works reliably under many conditions, through many tests, and across many production cycles. Large customers do not easily switch to a new substrate supplier because if the substrate fails, their entire product is affected. The validation process can take years. During that time, factories have already invested money and engineers have already worked hard, but major revenue may still not arrive. That is why the West has often viewed glass substrates as a long-term research direction. Attractive, yes. Important, yes. But not urgent yet. China, meanwhile, may be looking at it differently. If the biggest barriers are time, money, and process learning, then a patient industrial investment model can create an advantage. If you move early, suffer early, and learn from failures early, then by the time the market truly needs the technology, the first mover already has production data that latecomers cannot immediately buy with money. And this is exactly where the race becomes more intense, because China is not the only one trying to dominate the future. Intel, Samsung, TSMC, Corning, and the glass substrate race. What makes this story even more important is that the giants are not standing outside the race. Intel is one of the companies speaking most openly and aggressively about glass substrates. In 2023, Intel announced one of the first glass substrates for next-generation advanced packaging, with plans to bring it to market in the second half of this decade. Intel said this technology could help continue scaling Moore's Law and move toward the goal of 1 trillion transistors in a single package by the year 2030. That shows Intel understands the problem very clearly. After years of being overtaken by TSMC in advanced chip manufacturing, Intel is trying to return through a broader strategy. Not just nodes, but packaging, foundry systems, chiplets, EMIB, Foveros, and new substrate materials. If Intel can lead in glass substrates, it can create a different kind of advantage, one that does not depend entirely on the race to shrink transistors. Samsung cannot stay outside either. As a group with chip manufacturing, memory, packaging, and electronic materials capabilities, Samsung has a very clear reason to care. Future AI chips need HBM. They need logic. They need large packages. And Samsung wants a role in many layers of that value chain. If glass substrates become an important foundation for AI accelerators, Samsung cannot allow Intel, TSMC, or China to take that position first. TSMC is in a more special position. Right now, TSMC is extremely strong in advanced packaging with CoWoS, a technology widely used for AI chips, especially products serving NVIDIA and other major customers. But current success also creates a difficult situation. When you are leading with an ecosystem that already works very well, you do not necessarily want to rush into breaking it. TSMC can wait for the right moment to move to a new material, but if it waits too long, others may gain experience first. Corning is also an important name to watch. This American company has a long history in glass, ceramics, and optical materials. Corning has been involved in advanced semiconductor packaging with glass solutions, including glass carriers and technologies related to through-glass vias in the advanced packaging space. If the race shifts toward materials, Corning has very deep expertise. But material expertise does not automatically become an advantage in large-scale semiconductor substrate production. The company that combines material science, process engineering, customers, and volume first will hold the real advantage. And it is not just the United States. South Korea, Taiwan, and China. Japan also has notable efforts. Rapidus is reportedly studying panel-level packaging on glass substrates for next-generation processors, using large glass panels for AI and high-performance computing, even though this effort is still in its early stage and carries many risks. Looking at the bigger picture, this is no longer a single-track race. It is more like a multi-layer chessboard. The United States has Intel, Corning, CHIPS Act funding, and a powerful chip design ecosystem. South Korea has Samsung, SK Group, and packaging materials capabilities. Taiwan has TSMC, a leading packaging supply chain, and the world's largest AI customers. Japan has materials, expertise, and ambitions to revive its semiconductor industry. China has a massive market, state capital, large-scale glass manufacturing capability, and very strong strategic motivation. So, who has the advantage? The answer is not simple. Intel has technology and a clear public roadmap. TSMC has customers and today's packaging ecosystem. Samsung has vertical integration in memory, Corning has materials, China has the ability to mobilize industry and learn quickly if enough capital is available. But in a field like glass substrates, advantage does not only come from patents, it comes from yield, qualification, production processes, and data accumulated over time. That is why a first mover can build a moat. Once a major customer has qualified a substrate supplier and designs its next-generation chips around that supplier's specifications, switching to another source is no longer a simple purchasing decision. It can require redesign, retesting, requalification, and accepting new risks. In semiconductors, risk is very expensive. So, in the end, the biggest question remains: is this technology truly powerful enough to change the future? Whoever controls the foundation controls the game in next years. Over the next few years, glass substrates may not appear in consumer life in a way people can easily notice. You'll not walk into a store and see a laptop box saying, "Built with next-generation glass substrate." You also will not hear ordinary users talking about TGV or interconnect density. But inside data centers, where every percent of performance and every watt of power has real value, glass substrates could make a very real difference. If this technology reaches large-scale production, AI chips could be packaged with more chiplets, denser connections, more stable signals, and better scalability. That could help companies build stronger accelerators for AI, scientific simulation, autonomous vehicles, humanoid robots, defense systems, and cloud computing. End users may never see the glass substrate, but they will feel the indirect impact. Faster AI, smarter services, better self-driving systems, smoother robot responses, and devices that depend more and more on powerful chip infrastructure. However, we also need to be careful. Just because someone invests $1 billion does not mean victory is guaranteed. Glass substrates still have to overcome manufacturing, yield, cost, qualification, and customer trust. If yield is low, prices will be too high. If reliability is not strong enough, customers will not take the risk. If organic substrates and silicone interposers continue improving, glass substrates may take longer to become mainstream. And if Intel, Samsung, TSMC, or other competitors accelerate faster, China may not easily take the lead. But what matters is that the race has shifted direction. In the past, everyone asked, who has the smallest node? Who has EUV? Who has the most advanced fab? Now the questions are expanding. Who has the best packaging? Who has the most stable substrate? Who can connect the most chiplets at the most reasonable cost? Who can produce the largest packages while keeping yield high? These are the questions that will decide the future of AI hardware. For the United States, this is both a warning and an opportunity. America still has leading companies, major capital, and the strongest chip design customers in the world. The U.S. government has also supported advanced packaging, including a proposed $75 million grant for Absolix to build a glass substrate production facility in Georgia for high-performance computing and defense. But if America focuses only on front-end fabs and underestimates packaging and substrate materials, it could miss an important layer of the value chain. For China, glass substrates are a strategic path. They do not fully replace the need for advanced chips, but they can help China move into a critical link of AI hardware. If global chip designers one day have to depend on substrates made in China, that would become a very different kind of industrial power. Not as loud as owning EUV machines, not as visible as owning a 2-nanometer fab, but potentially very deep and very hard to replace. The future of the chip industry may not be one single race. It will be a combination of many smaller races: transistors, chiplets, memory, packaging, substrates, power delivery, cooling, and software. The country or company that controls more layers will hold the stronger position. And in that picture, glass substrates could become one of the most important foundation layers. When people hear the phrase chip war, very few think about glass. We think about silicon. We think about giant clean rooms. We think about ASML, TSMC, Intel, Samsung, and NVIDIA. We think about numbers like 3 nanometers, 2 nanometers, billions of transistors, and hundreds of billions of dollars in investment. But sometimes, the biggest turning point is not where everyone is looking. It is in the silent foundation underneath, where the entire system has to stand firm. Glass substrates matter because they touch a problem the chip industry cannot avoid forever. AI chips are getting larger, hotter, more complex, and more connection-hungry. Organic substrates have served the industry for a very long time, but as AI pushes hardware to the limit, a new foundation may become necessary. Intel, Samsung, TSMC, Corning, Rapidus, and Chinese companies are all seeing that signal. The difference is that each side is entering the race with its own strengths, its own fears, and its own strategy. If China has truly invested more than $1 billion in this direction, the story is not just about money. It is a statement that China does not want to keep chasing forever on the same battlefield controlled by others. It wants to find another battlefield where glass manufacturing experience, state capital, industrial scaling power, and time spent learning can turn into an advantage. But whether that advantage is large enough to change the balance of power is something no one can say for sure yet. Maybe glass substrates will become a real revolution in advanced packaging. Maybe they will need many more years to overcome yield, cost, and market trust barriers. Maybe China will move ahead in some segments. Or maybe Intel, Samsung, TSMC, or a Western Materials Alliance will accelerate and stop the gap from widening. But one thing is already clear. The race is no longer only about who can print smaller transistors. It is shifting toward a much bigger question. Who can build the best foundation for the next generation of AI chips? And that is what makes this story worth watching. Because over the next few years, what decides a nation's AI power may not be only the fastest GPU or the most expensive factory. It may be a thin, flat, stable glass substrate, sitting quietly underneath the most powerful chips in the world. So what do you think? Is glass substrate truly the turning point that will change the direction of the chip war? Or is it still a promising technology that is too early to judge? Does the West still have enough time to catch up? Or has China already started digging an industrial moat that will be very hard for rivals to cross? Leave your thoughts in the comments below. And if you found this video useful, do not forget to hit like, subscribe, and turn on notifications to keep following the major technology stories quietly shaping the future.